Tonight, we are going to confront one of the most seductive ideas in all of space travel, the sleeper ship. A spacecraft that carries human beings across the void, not by keeping them awake for the journey, but by putting them to sleep. No boredom, no aging, no generations living and dying aboard. Just quiet bodies in quiet pods, drifting between the stars while the machines do everything. It sounds like the perfect solution. But there is a question buried inside this idea that almost nobody talks about. How long could a sleeper ship actually keep its passengers alive? Not awake, not active, preserved. Because in deep space, sleeping does not mean safe. It means helpless. And the ship that carries you becomes the only thing standing between your body and oblivion. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Also, before we begin, we're now live on Spotify. The link's in the description if you would like to listen to us wherever you are. Now, are you comfortable? Let's begin. The nearest star beyond our own sun is Proxima Centauri. It sits roughly 25 trillion miles away. At the speed of Voyager 1, the fastest object humanity has ever sent toward interstellar space, moving at about 38,000 miles per hour. The journey would take approximately 70,000 years. If you want a star system with better odds of harboring a world worth visiting, you're looking at targets 10, 20, 50, or 100 light years away. The distances grow fast, and physics does not soften them for our convenience. Even with the most advanced propulsion systems anyone has seriously proposed, nuclear pulse propulsion, fusion drives, antimatter engines, the fastest we could realistically push a crewed spacecraft is a small fraction of the speed of light. A few percent, if everything goes right. At 5% of the speed of light, Proxima Centauri is still roughly 85 years away. A more distant target could be a century away, or 2, or 3. These are not commute times. These are spans that stretch across entire human lifetimes, and well beyond them. There is no faster option on the horizon. Warp drives remain theoretical constructs with no confirmed engineering pathway. Wormholes exist in the mathematics of general relativity, but have never been observed in any form. The speed of light is not a barrier we are close to breaking. So if humanity ever wants to send living people, not probes, not radio signals, but actual human beings, to another star, the journey will almost certainly outlast any single human life. That is the central problem of interstellar travel. Not propulsion alone, not shielding, not navigation. Time. The journey takes longer than a person can live. And every solution to interstellar travel is a proposed answer to the same question. What do you do when the journey outlasts the people who board the ship? One answer is the generation ship. You build something enormous, a self-contained world, and you fill it with enough people to sustain a population across centuries. Babies are born, children grow up, adults grow old and pass away, and the descendants of the original crew, people who have never set foot on Earth and never will, eventually arrive at the destination. The generation ship does not cheat time, it accepts it. It carries an entire civilization through the void and asks that civilization to keep itself together across the ages. The generation ship is a real and serious concept that researchers have studied extensively. But it comes with staggering challenges. You need a population large enough to maintain genetic diversity across centuries, potentially tens of thousands of people. You need biological life support systems that function as complete ecosystems. You need governance structures that remain legitimate for people who never agreed to the mission. You need food production, medical care, manufacturing capability, conflict resolution, and a culture strong enough to sustain commitment to a goal that most of the people who ever live aboard will never see fulfilled. Every one of those requirements hides a cascade of unsolved problems. The generation ship is possible in principle, but it asks more of human society than any civilization has ever delivered inside a sealed container with no outside help. So people looked at the generation ship with all its biological and social and political complexity and asked a different question. What if you did not have to keep people alive and active for the whole journey? What if you could put them to sleep? That is the sleeper ship. And as a concept, it is elegant almost to the point of seduction. A sleeper ship carries its passengers not as a living community, but in a state of biological suspension. Torpor, hibernation, cryosleep, whatever you call it, the principle is the same. You reduce the human body to a state of minimal or zero metabolic activity. The heart slows or stops, body temperature drops, sometimes dramatically. Cellular processes halt or nearly halt. The person does not think, does not dream, does not age normally, does not eat or drink or breathe at a normal rate. They are preserved, held in biological pause, while the ship crosses the distance and the decades and the centuries pass outside without touching them. The appeal is immediate and profound. A sleeper ship eliminates most of the problems that make a generation ship so difficult. You do not need a self-sustaining civilization. You do not need tens of thousands of people. You do not need agricultural decks or schools or governance structures for people who live their entire lives aboard. You do not need to solve the genetic bottleneck problem because the passengers are not reproducing during the journey. You do not need to address the psychological devastation of spending a lifetime sealed inside a metal world with no horizon and no outside. A sleeper ship sidesteps all of that. The passengers close their eyes on the day of launch and open them at the destination. For them, the journey is instantaneous. For the ship, it lasts decades or centuries. But the ship does not care about boredom, about politics, about existential dread. The ship is a machine, and machines, presumably, do not mind the dark. That is the promise, and stated that way, it sounds almost too good to be true, which is the first signal that we need to look much more carefully at what this idea actually requires. Because the sleeper ship depends on a single foundational assumption, that we can put human beings into a state of prolonged biological suspension and then bring them back. Not just alive, but functional. Not just breathing, but thinking. Not just surviving, but recovered well enough to step off the ship and begin a new life on a world they have never seen. And the honest answer, as of right now, is that we cannot do this. Not for months, not for years, certainly not for decades or centuries. Human hibernation, in the sense that a sleeper ship would require, is not a solved technology. It is not even close to solved, and the gap between what current science can achieve and what interstellar cryosleep would demand is not a gap that better engineering can casually close. It is a chasm that spans entire fields of biology we do not yet understand. Let us start with what nature has already figured out. Some animals hibernate. This is real, documented, well-studied biology. Bears enter a state of torpor during winter months. Their heart rate drops from roughly 40 beats per minute to as low as 8. Their body temperature decreases modestly. A few degrees, not the dramatic plunge that science fiction often imagines. Their metabolism drops by approximately 75%. They do not eat, drink, urinate, or defecate for months. Their muscles and bones lose surprisingly little mass, despite the prolonged immobility. Their bodies recycle metabolic waste internally with an efficiency that medical researchers find genuinely remarkable. Ground squirrels go even deeper. During hibernation, their body temperature can drop to just above freezing, sometimes to -2 or -3 degrees Celsius. Their heart rate drops to as low as 5 beats per minute. Their metabolic rate plummets to roughly 2% of their active baseline. They cycle between deep torpor bouts and brief interboot arousals, periods of a few hours where they warm up, adjust physiologically, and then cool back down. These arousals appear to be essential. Scientists believe they serve some repair or maintenance function that even hibernating bodies require. Dwarf lemurs of Madagascar are the only primates known to be obligate hibernators. They enter torpor seasonally, lowering their metabolic rate dramatically and surviving on stored fat for months. They are the closest evolutionary relatives to humans that naturally hibernate, and their biology has attracted intense interest from space medicine researchers, precisely because of that proximity. If a primate can do this naturally, the thinking goes, perhaps the biological machinery for torpor is not entirely absent in humans. Perhaps it is merely dormant. Perhaps it can be activated. That perhaps is doing enormous work. The distance between a lemur in a tree hollow and a human in an interstellar pod is one of the largest unsolved problems in biology. Humans do not naturally hibernate. We do not enter torpor. Our bodies do not possess, as far as current science can determine, a simple switch that reduces metabolism to hibernation levels safely and reversibly. We are large-bodied homeotherms. Our brains are exquisitely sensitive to temperature changes, oxygen deprivation, and metabolic disruption. Our organ systems have different tolerances for cooling, for reduced blood flow, for altered chemistry. The heart, the brain, the kidneys, the liver, they do not all respond the same way to the same intervention. Cooling a human body uniformly without causing cardiac arrest, without triggering ice crystal formation in tissues, without creating chemical imbalances that damage cells, is extraordinarily difficult. Medical hypothermia does exist. Surgeons use it routinely. During certain cardiac procedures, a patient's body temperature is lowered to around 28 degrees Celsius, roughly 82 degrees Fahrenheit, to reduce oxygen demand and protect the brain during periods when blood flow is temporarily interrupted. Patients can survive this level of cooling for hours. It is a proven and life-saving technique, but it requires constant monitoring by a medical team. It is performed in a hospital with full life support available, and the cooling is modest, the duration is short, and the rewarming is carefully controlled. This is not hibernation. It is a brief, managed physiological intervention with a full medical infrastructure standing by. The question is whether we can go further. Deeper cooling, longer duration, less monitoring, with the goal of suspending a human being for not hours, but weeks, months, years, or longer. NASA has been funding research into this question. At the University of Pittsburgh, studies support through the Translational Research Institute for Space Health have achieved something genuinely interesting. Healthy human volunteers received controlled doses of a sedative called dexmedetomidine, an alpha-2 adrenergic agonist, which produced a safe, reversible reduction in metabolic rate of approximately 20%, accompanied by a slight lowering of core body temperature. The subjects entered a drowsy, sleep-like state, a condition researchers call quasi-torpor. They could be roused briefly to eat, drink, or use the restroom. They did not require full sedation or invasive life support. This is real, documented, and genuinely promising, but it is also a 20% metabolic reduction lasting hours, achieved in a clinical setting with constant medical supervision. The gap between this and the 98% metabolic reduction that some hibernating ground squirrels achieve for months at a time, without supervision in a tree burrow, is enormous. The European Space Agency has been pursuing this question from its own angle. ESA's Concurrent Design Facility conducted a detailed study linking the biology of hibernation to the engineering requirements of spacecraft design. They concluded that inducing torpor in crew members could meaningfully reduce the payload mass of a deep space mission by cutting requirements for oxygen, food, and water. But they also concluded that torpor would require artificial intelligence-assisted monitoring of both the crew and the spacecraft, and that the biological and engineering challenges are deeply intertwined. You cannot solve one without addressing the other. NASA's STASH project, studying torpor in animals for space health in humans, was selected under the 2024 NASA Innovative Advanced Concepts Program. STASH proposes to build the infrastructure needed to study hibernation in rodents aboard the International Space Station, because one of the critical unknowns is how torpor behaves in microgravity. Hibernation has never been studied in space. We do not know if the biological mechanisms that regulate torpor on Earth function the same way without gravity. STASH is designed to answer that foundational question. It is a first step, not a solution. A first step toward acquiring the fundamental knowledge that would eventually be needed to even consider human applications. A recent and significant paper published in 2026 in the journal Current Stem Cell Reports reviewed the current understanding of human torpor potential and proposed using human organoid systems, lab-grown miniature organ models, to study how human tissues respond to torpor-like conditions. The paper noted that dwarf lemurs remain the only obligate primate hibernators, and that findings from hibernating mammals, particularly brown bears, offer translatable insights but remain far from direct human application. It also cited research showing that synthetic torpor in rats provides some degree of radio protection, which is directly relevant to space travel. But the authors were careful to emphasize that human torpor trials are not imminent. ESA researcher Jennifer Ngo An, a co-author on the agency's hibernation strategy, has estimated that the first human torpor trials could take place in the mid-2030s, depending on funding, roughly a decade away. Even that timeline is optimistic, and refers to short-duration trials, not long-duration suspension. So that is torpor. Light metabolic suppression in humans has been demonstrated for hours. Deep metabolic suppression has been demonstrated in small animals for months. The bridge between these two realities has not been crossed, and the researchers closest to the work describe a decade as a realistic timeline for the first cautious human experiments. But a sleeper ship for interstellar travel does not need torpor for hours or days. It needs preservation for decades or centuries, and that requires something far more radical than torpor. That requires cryopreservation. Cryopreservation is the preservation of biological material at extremely low temperatures. It is routine medicine for certain applications. Human sperm, egg cells, and embryos are cryopreserved every day in fertility clinics around the world. These are small collections of cells. They can be cooled rapidly, stored in liquid nitrogen at negative 196 degrees Celsius, and thawed successfully with high viability rates. This works because the cells are tiny, and the cooling and warming can be controlled precisely at that scale. The problem is ice. When biological tissue is cooled slowly, water inside and between cells forms ice crystals. Those crystals are sharp, rigid structures that puncture cell membranes, shear cellular components, and cause catastrophic mechanical damage at the microscopic level. Cool a human organ conventionally, and the ice formation destroys it. This is why you cannot simply freeze a person and expect to thaw them later. The ice does not just pause the biology, it shreds it. Vitrification offers an alternative. Instead of allowing water to freeze into crystals, you replace the water in the tissue with high concentrations of cryoprotective agents, chemical compounds that prevent ice formation. When cooled rapidly enough, the tissue transitions into a glassy, amorphous solid state rather than a crystalline one. No ice crystals form. The biological structure is preserved in glass, suspended in a state that is technically a solid, but retains the disordered molecular arrangement of a liquid. This is vitrification, and it is genuinely promising. In 2023, a team at the University of Minnesota achieved a landmark result. They vitrified rat kidneys, stored them at negative 150 degrees Celsius for up to 100 days, and then rewarmed them using a technique called nanowarming. In nanowarming, iron oxide nanoparticles are infused into the organ's vasculature before vitrification. During rewarming, an alternating magnetic field heats the nanoparticles rapidly and uniformly, bringing the entire organ back to temperature without the slow, uneven warming that causes ice crystallization during the thaw. The rewarmed kidneys were transplanted into rats whose own kidneys had been removed. The transplanted organs restored full, life-sustaining renal function. This was the first time a cryopreserved organ had been successfully stored long-term and then used to sustain life after transplantation. This is a genuine breakthrough. It is also a rat kidney, a single organ roughly the size of a large grape, stored for 100 days. The distance from this result to the whole body cryopreservation of a living human being, with dozens of organ systems, each with different cryoprotectant tolerances, different cooling rates, different rewarming requirements, a brain with 100 billion neurons whose connections must be preserved with absolute fidelity. If the person is to wake up as themselves, that distance is staggering. A company called Until Labs, co-founded by researcher Laura Deming, has stated publicly that it believes human whole-body reversible cryopreservation is solvable. The company has raised over $100 million to pursue this goal. They have published work on recovering electrical activity from cryopreserved and rewarmed rodent neural tissue, and on scaling nanowarming systems to organ-level applications. And even they frame whole-body reversible cryopreservation as a long-term research goal, not a near-term deliverable, because the honest assessment, as of right now, is this. We can put human cells into indefinite cryogenic storage and recover them. We can put small animal organs into cryogenic storage for months and recover them. We have achieved light metabolic suppression in humans for hours. We have achieved deep torpor in small, non-hibernating mammals for hours. We have never placed a human being into prolonged metabolic suspension of any kind and brought them back. Not for a week, not for a month, not for a year. Certainly not for a century. The gap between current science and what a sleeper ship would need spans three distinct categories of challenge. The first is inducing the state. Finding a method to safely reduce human metabolism to near zero or transition the body into a vitrified state without killing the patient in the process. The second is maintaining the state, keeping the body in stable suspension for the duration of the voyage without degradation, without slow chemical changes that accumulate invisibly over decades, without the cryoprotectant itself causing toxicity over long exposure. The third is reversing the state, bringing the person back with full biological and cognitive function intact, their memories preserved, their personality unchanged, their body capable of standing up and walking off the ship. Each of these challenges is one of the hardest unsolved problems in medicine, and together they represent a frontier that may take decades or centuries to cross. And yet, even if we imagine that all three are eventually solved, that future science cracks every one of these problems and gives us a reliable, reversible method for placing human beings into indefinite biological suspension, even then, the sleeper ship's problems are only half addressed, because the biology is only the human side of the equation. There is an entire other side that has nothing to do with metabolism or vitrification or cryoprotectant chemistry. It has to do with the ship. A sleeper ship full of preserved human bodies is not a passive container drifting through empty space. It is an active machine performing dozens of critical functions simultaneously, every second of every hour of every day for decades or centuries, without a single conscious human being aboard to monitor it, maintain it, diagnose its problems, or repair its failures. On a normal crewed spacecraft, human beings are the most important system. They are the adaptive layer. They notice when something sounds wrong. They smell an electrical fire before the sensor trips. They look at a readout and feel that something is off before the algorithm flags it. They improvise. They jury rig. They solve problems that no one anticipated because human intelligence is flexible in a way that no automated system has ever matched. A sleeper ship has none of that. The crew is unconscious. They cannot hear the alarm. They cannot smell the smoke. They cannot look at a gauge and recognize that the reading does not make sense. They are bodies in pods, biologically inert, completely dependent on the systems surrounding them. If the power flickers, they do not notice. If the temperature drifts, they cannot adjust it. If a seal fails and atmosphere leaks from a compartment, they cannot patch it. If the navigation system drifts off course by a fraction of a degree, they cannot correct it. If the medical monitoring system misreads a sensor and fails to detect that a passenger's preservation is degrading, they cannot intervene. Everything the crew would normally do, everything that keeps a crewed spacecraft alive, now falls entirely on the machine. The ship does not carry a crew. The ship is the crew, and the passengers are cargo. Precious, fragile, irreplaceable cargo that must be delivered alive at the other end. But cargo nonetheless. This is the conceptual shift that most discussions of sleeper ships gloss over too quickly. Putting humans to sleep does not make interstellar travel easier. It makes it different. It trades one set of problems for another. The generation ship's problems are human. Psychology, governance, genetics, social cohesion, knowledge transmission, cultural meaning. The sleeper ship's problems are mechanical. Power, cooling, radiation, maintenance, autonomous repair, sensor reliability, software integrity, and the terrifying fragility of a revival process that has never been attempted. The sleeper ship does not escape the brutal machine survival problem of deep space. It concentrates that problem into its purest form. Because on a generation ship, if a system fails, there are people awake to fix it. On a sleeper ship, if a system fails, there is no one. Just the ship and the silence, and the slowly accumulating consequences of a problem that no one alive can address. That is what we need to examine next. Not the biology of sleep, but the engineering of the ship that must keep sleeping passengers alive in the most hostile environment known to exist. The question is not whether we can put humans to sleep. The question is whether a machine can do everything that needs to be done while they are under, and whether it can do it long enough to matter. Think about what happens aboard the International Space Station on any given day. There are roughly half a dozen people up there at any time, and those 6 people spend a significant portion of their waking hours on maintenance. They replace filters, they repair exercise equipment, they troubleshoot cooling loops, they patch software, they swap out failed components, they monitor carbon dioxide levels, water recycling systems, atmospheric pressure, they inspect seals, clean vents, calibrate instruments. The station is only about the size of a large house, and it orbits just 250 miles above Earth, close enough that resupply ships arrive every few weeks carrying spare parts, fresh food, and replacement hardware. And still, keeping it running requires constant, skilled human attention. Now remove the humans, remove the resupply ships, remove the proximity to Earth. Send the station not 250 miles up, but 25 trillion miles out. And instead of keeping 6 astronauts comfortable and productive, ask it to keep dozens or hundreds of biologically suspended human bodies preserved at precise temperatures, monitored at the cellular level, shielded from radiation, and ready for revival at the other end. That is what a sleeper ship must do. And every system required to do it must work simultaneously, without interruption, for the full duration of the voyage. There is no shift change. There is no maintenance crew. There is no resupply. There is only the ship, its automation, and the passengers who cannot help themselves. Let us begin with the most fundamental requirement: power. A sleeper ship needs energy for everything. Not the enormous energy budget of a generation ship supporting thousands of active people, but a budget that is still substantial and absolutely continuous. The preservation pods require cooling or temperature maintenance. The medical monitoring systems require electricity. The radiation shielding, if it is active rather than passive, requires power. Navigation instruments need power. Communication systems need power. The ship's computers, running the autonomous control software that manages every other system, need power. And whatever robotic or automated repair capability the ship carries needs power when called upon. In deep space, none of those options exist. The ship carries its own power source from the moment of launch, and that source must last the entire voyage. There is no refueling. There is no grid. There is no one to call. Solar panels are useless beyond Mars. By interstellar distances, the solar flux is negligible. A sleeper ship needs nuclear power. The most proven deep space power technology is the radioisotope thermoelectric generator. These devices convert heat from the natural radioactive decay of an isotope, typically plutonium-238, into electricity using thermocouples. They have no moving parts. They require no active management. They produce power continuously for decades. The Voyager probes, launched in 1977, each carry 3 radioisotope thermoelectric generators that's still functioning nearly 50 years later. Cassini operated on them for roughly 20 years. New Horizons is still running on 1 deep in the Kuiper belt. That reliability is remarkable, but it comes with a hard physical limit. Plutonium-238 has a half-life of approximately 87.7 years. That means after roughly 88 years, the isotope has decayed enough that the generator produces only half the power it started with. After another 88 years, it is down to a quarter. After 3 half-lives, roughly 264 years, it produces 1/8 of its initial output. The decay is relentless and cannot be reversed or slowed. The Voyager probes illustrate this beautifully and painfully. At launch, each probe's generators produced about 470 watts of electrical power. Today, nearly 5 decades later, that output has dropped to roughly 220 watts. NASA has been progressively shutting down instruments and systems aboard the Voyagers for years, trimming power consumption to stay below the declining supply. They expect to lose the ability to operate any scientific instruments within the next few years. The probes will eventually go silent, not because their structure failed or their computers crashed, but because the power simply ran out. For a sleeper ship, this creates a stark engineering constraint. If your voyage lasts 50 years, radioisotope generators are workable. You will have lost some power, but careful design can accommodate the decline. If your voyage lasts 200 years, you are operating on roughly 25% of your initial power budget for the final decades, and your systems must be designed from the start to function at that reduced level. If your voyage lasts 500 years, you're trying to run a spacecraft on roughly 2% of its original power output. That is not a graceful degradation. That is a slow death. Nuclear fission reactors offer much higher power output than radioisotope generators. A well-designed fission reactor burning enriched uranium or thorium can produce kilowatts or even megawatts of electrical power, orders of magnitude more than any radioisotope system. And with sufficient fuel loading, a fission reactor can theoretically operate for decades or longer. But fission reactors are not passive. They are active, complex systems with moving parts, control mechanisms, coolant loops, moderators, and shielding. They require management. On Earth, nuclear reactors are operated by teams of trained engineers who monitor performance, adjust control rods, manage coolant flow, replace components, and respond to anomalies. On a submarine, a nuclear reactor runs for 20 to 25 years between refuelings, maintained by a crew of specialists who live alongside it. A sleeper ship has no crew of specialists. The reactor must run itself. It must monitor its own neutron flux, manage its own thermal output, detect and respond to its own anomalies, and do all of this without human oversight for the entire voyage. Autonomous reactor operation for years is within the reach of current technology. Autonomous reactor operation for decades, with no maintenance access, in the radiation environment of deep space, where the control electronics themselves are subject to degradation, that is a much harder problem. An autonomous reactor operation for centuries is something no engineer alive today would be willing to guarantee. The power system defines the outer limit of how long a sleeper ship can function. When the power runs out, everything stops. The cooling stops. The monitoring stops. The navigation stops. The passengers begin to warm or drift or degrade, and there is nothing anyone can do about it because there is no one awake to notice, and no reserve to draw on. Power is not one system among many. It is the foundation beneath every other system, and it is the first system whose physics imposes a hard expiration date on the mission. Assume the power problem is managed. The next question is thermal control. The passengers aboard a sleeper ship are preserved at a specific temperature, and that temperature must remain stable within narrow tolerances for the entire voyage. How narrow depends on the preservation method. If the crew is in light torpor, their body temperature might be maintained at around 32 to 34 degrees Celsius. The tolerance is a few degrees. Drift much below that and you risk cardiac complications. Drift above and the metabolic suppression loses its effect. If the crew is in deep hypothermia, temperatures might be around 4 to 10 degrees Celsius. If they are vitrified, they are stored at approximately negative 150 degrees Celsius, or colder, in a glassy solid state. At vitrification temperatures, the tolerance is brutally tight. If the temperature rises even modestly, the glassy state destabilizes and ice crystals begin to form inside the tissue. This is called devitrification, and it is lethal. The very ice formation that vitrification was designed to prevent occurs during the rewarming if the process is not perfectly controlled. Even small temperature excursions, sustained for hours, can initiate crystal nucleation that damages tissue irreversibly. The thermal control system must maintain this stability for decades or centuries. In space, thermal management is fundamentally different from thermal management on Earth. There is no air to carry heat away. There is no convection. The only way to reject waste heat in space is through radiation, emitting infrared photons from large radiator panels into the void. And the only way to prevent unwanted heat gain or loss is through insulation and active thermal management, heaters, coolers, heat pipes, and fluid loops that move thermal energy from where it is not wanted to where it can be radiated away. These radiator panels are among the most exposed components on the spacecraft. They face the external environment directly. Over decades of travel through the interstellar medium, they are subject to micrometeorite impacts, cosmic dust erosion, and the slow degradation that comes from thermal cycling, as the ship's orientation changes relative to heat sources and heat sinks. The radiator surfaces accumulate damage, their emissivity changes, their efficiency drops, and no one is awake to inspect them, clean them, or replace degraded panels. Inside the ship, the cooling systems themselves are mechanical. They contain fluids, pumps, valves, heat exchangers. Every one of these components has a finite service life. Pump bearings wear, seals dry and crack. Coolant fluid can degrade chemically over long periods, losing its thermal properties or becoming corrosive. A slow leak in a coolant line might lose only a few milliliters per year, completely undetectable by any alarm. But over 30 years, that is liters. Over a century, the system is dry. The more realistic threat to thermal control is not gross failure, but drift. A slow, gradual shift in temperature stability that stays within alarm thresholds for years, while the damage to preserved tissue accumulates silently below the resolution of the monitoring systems. By the time the drift becomes large enough to trigger an alert, the passengers may have already sustained irreversible cellular damage. The ship does not know this. The passengers cannot report it. And the automated systems were never designed to detect damage at the biological level, only at the engineering level. This leads us to radiation, which is perhaps the most relentless of all the environmental threats a sleeper ship must manage. In deep space, beyond the protective magnetic field of any star, the radiation environment is dominated by galactic cosmic rays. These are high-energy particles, mostly protons, but also heavier nuclei including helium, carbon, oxygen, silicon, and iron, accelerated to enormous velocities by supernova remnants and other violent astrophysical processes across the galaxy. Some of these particles carry energies so high that they penetrate virtually any practical amount of shielding. A centimeter of aluminum does not stop them. 10 centimeters does not stop them. They pass through the hull, through the ship's interior structure, through the walls of the preservation pods, and through the bodies of the sleeping passengers, depositing ionizing energy in tissue as they go. The biological effects of this radiation are cumulative. Every particle that passes through a cell has a chance of damaging DNA, disrupting cellular machinery, or triggering mutations that could lead to cancer. On Earth, we are shielded by both the planet's magnetic field and its thick atmosphere, which together absorb the vast majority of galactic cosmic rays before they reach the surface. The radiation dose at sea level from cosmic sources is roughly 0.3 millisieverts per year. Aboard the International Space Station in low Earth orbit, the dose is roughly 150 to 200 millisieverts per year, because the station sits above most of the atmosphere and within the lower fringes of the magnetosphere. In deep interstellar space, outside any planetary magnetosphere, the dose from galactic cosmic rays is estimated at roughly 300 to 400 millisieverts per year, depending on shielding configuration and the phase of the solar cycle. Over a 3-year Mars mission, an astronaut would accumulate roughly 1 to 1.2 sieverts, enough to measurably increase lifetime cancer risk. Over a 50-year interstellar voyage, a sleeping passenger would accumulate roughly 15 to 20 sieverts if unshielded. That is a lethal or near-lethal cumulative dose. Even with substantial shielding, the exposure over decades is significant. And unlike a conscious crew member who can take shelter during a solar particle event or manage their exposure through behavioral adjustments, a sleeping passenger has no behavior to adjust. They absorb whatever the ship's shielding does not stop. There is one genuinely promising finding in this area. Research published in recent years has shown that synthetic torpor, the artificially induced hibernation-like state studied in rats, appears to offer some degree of radio protection. In studies where rats were irradiated with high-energy heavy ions while in a state of synthetic torpor, their liver and reproductive tissues showed less radiation damage compared to rats irradiated while awake. The mechanism is not fully understood, but may relate to the reduced metabolic rate itself. When metabolism is suppressed, fewer free radicals are produced, DNA repair pathways may be altered, and the cellular environment may be less vulnerable to the secondary damage that radiation triggers in metabolically active tissue. This is encouraging, but it is early-stage animal research. It has been demonstrated in rats, not humans. The degree of protection is partial, not absolute, and it has been studied over hours, not decades. Whether torpor-induced radio protection would meaningfully reduce cumulative damage over a 50-year voyage is an open question with no current answer. The prudent assumption for any sleeper ship design is that radiation remains a serious and unresolved threat that shielding alone cannot fully mitigate. Shielding options exist, but involve painful trade-offs. Water is an excellent radiation absorber for certain particle types. Storing the ship's water supply in tanks surrounding the habitation and preservation areas provides dual-purpose mass. Polyethylene and other hydrogen-rich polymers are effective against proton radiation. But every kilogram of shielding is a kilogram that must be accelerated to interstellar velocity and later decelerated at the destination. Mass is the fundamental currency of spaceflight, and shielding demands enormous quantities of it. Active magnetic shielding, generating a powerful magnetic field around the ship to deflect charged particles, has been proposed, but requires superconducting magnets, substantial power, and engineering complexity that introduces its own failure modes. The radiation problem does not have a clean solution. It has only a spectrum of compromises, each trading mass, power, and complexity against a dose reduction that is meaningful but never complete. The hull itself is a survival system that deserves separate attention because it is the outermost link in the entire dependency chain. Everything else, the power system, the thermal control, the preservation pods, the passengers, all of it sits inside the hull. If the hull fails, nothing else matters. A sleeper ship traveling at even a few percent of the speed of light encounters the interstellar medium at relative velocities that transform harmless specks into projectiles. A grain of dust weighing a fraction of a milligram, striking the hull at 3% of light speed, carries kinetic energy equivalent to several kilograms of high explosive. The ship's forward-facing surfaces absorb these impacts continuously across the entire voyage. Not a single dramatic collision, but an unending rain of microscopic strikes, each one too small to trigger an alarm, but each one removing a tiny fraction of the hull's protective material. Over decades, the cumulative erosion is significant. Whipple shield layers, the thin outer bumper plates designed to fragment and disperse incoming particles before they reach the structural hull, slowly thin. The gaps between layers may accumulate debris from vaporized impacts, changing the shield's performance characteristics in ways that are difficult to model over very long periods. The structural hull beneath the shields develops microfractures from the thermal cycling that occurs as the ship rotates, as heat sources shift, as the forward face absorbs impact energy, and the aft face radiates into the cold of empty space. These microfractures are individually insignificant. Over a century, they propagate. Metal that was flawless at launch develops a fatigue profile that no one is awake to inspect. And the hull is not just a passive barrier, it is a pressure vessel. The inhabited and pod sections of the ship maintain an internal atmosphere, whether for torpid passengers who are still breathing or for the controlled inert environment surrounding vitrified bodies. That atmosphere exerts outward pressure on the hull continuously. A hull that has been slowly weakened by decades of micrometeorite erosion and thermal fatigue is a hull whose margin against pressure failure is narrower than the day it launched. The difference between a hull that holds and a hull that does not might come down to a single microfracture that grew 1 millimeter too far while no one was watching. On current spacecraft, hull integrity is maintained through regular inspection and repair. A sleeper ship has no astronauts to inspect and no ground team to consult. Automated hull monitoring, pressure sensors, strain gauges, possibly ultrasonic inspection systems would need to track structural health for the full duration. But these sensors are themselves subject to the drift and degradation that affects every instrument aboard. A strain gauge bonded to the hull may delaminate after 30 years, reporting normal stress in the section that is actually approaching failure. The ship believes the hull is sound. It may not be. Now consider the life support system, which on a sleeper ship operates in a mode that has no precedent in spaceflight history. If the passengers are in light torpor rather than full vitrification, they are still biologically active, just at a greatly reduced rate. They breathe slowly. They consume oxygen. They exhale carbon dioxide. Their cells produce metabolic waste products. The life support system must manage these outputs, scrubbing carbon dioxide, replenishing oxygen, managing humidity, maintaining atmospheric pressure, all in a minimal mode calibrated to the suppressed metabolic rate of the passengers. The challenge is that this minimal mode must be precisely calibrated and must remain so for the entire voyage. If the life support system overperforms, it wastes power and consumables. If it underperforms, even slightly, the imbalance accumulates. A carbon dioxide concentration that is 0.1% too high is harmless for a day. Over a month, it begins to affect blood chemistry. Over a year, it can cause tissue acidosis in patients whose bodies are too suppressed to compensate. Over a decade, the cumulative exposure could be lethal, and the passengers would never know it because they are unconscious. The same principle applies to oxygen levels, humidity, and trace contaminant management. Every atmospheric parameter must stay within tolerance for the duration, and the systems maintaining those parameters are mechanical. They have filters that clog, pumps that wear, sensors that drift. A sensor that reads carbon dioxide levels accurately at launch may read 5% low after 20 years of operation due to chemical degradation of its sensing element. The system thinks the atmosphere is fine. It is not. If the passengers are vitrified rather than in torpor, the atmospheric requirements change. Vitrified bodies are not breathing. They are solid. They do not consume oxygen or produce carbon dioxide. But the preservation chambers themselves must maintain a controlled environment, free from condensation, free from biological contamination, free from chemical reactions that could attack the cryoprotectant compounds infusing the tissue. The atmosphere surrounding a vitrified body must be dry, inert, and stable. Any moisture intrusion at cryogenic temperatures forms frost, and frost in contact with vitrified tissue can initiate the de-vitrification process that destroys cells. Even the outgassing of materials used in the pod's construction, plastics releasing volatile organic compounds over decades, could compromise the preservation environment. And this raises a problem that sits at the boundary between engineering and biology, one that is easy to overlook because it happens inside the pod rather than in the ship's corridors. The cryoprotectant solution itself is not permanent. Cryoprotectants are chemical compounds, typically mixtures of substances like dimethyl sulfoxide, ethylene glycol, or proprietary formulations designed to replace water in tissue and prevent ice formation during vitrification. They are chosen for their ability to form stable glasses at low temperatures. But they are still chemicals, and chemicals do not remain inert forever. Over months, the behavior of cryoprotectants is well characterized in laboratory settings. Over years, less so. Over decades, almost not at all. The longest cryopreservation experiments with functional recovery, the University of Minnesota's rat kidney study, lasted 100 days. What happens to cryoprotectant compounds over 30 years at negative 150 degrees Celsius is largely unknown. Slow chemical reactions do occur even at cryogenic temperatures, though at drastically reduced rates. Trace impurities in the solution, residual biological material from the tissue, microscopic particles shed from the pod walls, all of these can serve as nucleation sites or catalysts for reactions that were undetectable over months but become significant over decades. The cryoprotectant might slowly react with the materials of the pod itself. Metals, polymers, seals, and gaskets in contact with the solution for years could leach trace compounds into the fluid. These contaminants might be chemically inert at the concentrations present in year 1. By year 20, they could reach levels that alter the glass transition behavior of the solution. By year 40, they could begin to interact with the tissue they were designed to protect. And the tissue itself is not truly inert, even when vitrified. Biological molecules are large, complex structures. Proteins can denature slowly, even at very low temperatures. Lipid membranes can undergo subtle phase transitions. DNA, preserved in the glassy matrix, is still subject to the slow accumulation of radiation-induced strand breaks. And without active repair mechanisms running, those breaks persist. Each one is individually negligible. Over decades, they accumulate. The genome of a vitrified cell in year 50 is not identical to the genome of that same cell in year 1. Whether the difference matters for revival is unknown, because no one has ever tried to revive a cell after 50 years of vitrification. This is a problem that no sensor on the ship can detect. The temperature is correct. The pressure is stable. The pod environment reads nominal. But inside the glass, at the molecular level, the chemistry is slowly shifting. The cryoprotectant is aging. The tissue is accumulating damage that is invisible to every monitoring system the ship carries. And the only way to discover whether this damage is compatible with a revival is to attempt the revival itself. At that point, it is too late to do anything about it. Medical monitoring adds another layer. Each passenger must be individually monitored for the full duration. Vital signs, to the extent they exist in a torpid or vitrified state, must be tracked continuously. For torpid passengers, this means heart rate, respiratory rate, core temperature, blood oxygen saturation, brain activity, and ideally some measure of cellular health. For vitrified passengers, the monitoring focuses on temperature stability, structural integrity of the vitrified tissue, potentially using imaging systems that can detect microcracks or ice nucleation, and the chemical stability of the cryoprotectant solution. These sensors must remain accurate for decades, without the regular calibration, maintenance, and replacement that medical sensors on Earth receive. Sensor drift is not a theoretical concern. It is a documented reality in every engineering field that uses long-duration instrumentation. A temperature sensor that drifts by 1/10 of a degree per decade sounds trivially small. Over a century, that is a 1-degree error. For vitrified tissue, where the margin between preservation and devitrification can be measured in single degrees, that drift could be the difference between life and death. And the monitoring system mustn't only sense, but interpret. The ship's medical automation must determine whether a given reading represents normal variation, sensor error, or a genuine emergency. It must distinguish between a stable patient in deep torpor and a patient whose preservation is slowly failing. It must decide when to alert the ship's autonomous systems and when to remain silent. And it must make these decisions using software that was written before the voyage began, by engineers who could not anticipate every possible scenario. Navigation requires its own dedicated attention. In interstellar space, there are no GPS satellites, no ground stations, no reference beacons. The ship navigates by measuring the apparent positions of known stars and computing its location and velocity from those measurements. This technique, celestial navigation at interstellar scales, requires functioning optical instruments, precise star catalogues, and computational systems that can account for the changing appearance of the star field as the ship moves at significant fractions of light speed. As the ship travels, parallax shifts change the apparent positions of nearby stars. Doppler effects alter the color of starlight. Stars ahead of the ship are blue shifted. Stars behind are red shifted. The familiar constellations distort and eventually become unrecognizable. The navigation system must account for all of these effects, computing the ship's true position from a star field that looks nothing like the one visible from Earth. A navigational error that accumulates gradually, a systematic bias in the star tracker, a misalignment of the telescope optics due to thermal distortion or micrometeorite impact, could send the ship off course by fractions of a degree per decade. Over a century of travel, fractions of a degree translate into millions of miles of positional error at the destination. The ship could miss its target star system entirely, flying past at interstellar velocity with no way to stop or turn around. And the sleeping passengers would wake up, if they woke up at all, to find themselves not in orbit around a new world, but hurtling through empty space with nowhere to go and no fuel to get there. Course corrections require functional thrusters and fuel reserves. Every correction burns propellant that cannot be replaced. The ship must carry enough propellant for the planned corrections, plus a margin for unforeseen adjustments. And the propellant itself must remain chemically stable and physically contained for the entire voyage. Fuel tanks can develop slow leaks. Propellant can degrade. Thruster mechanisms can seize after decades of dormancy. Every component in the navigation and propulsion chain must work when called upon, potentially after years or decades of inactivity. Communication with Earth deserves mention, though its role changes fundamentally as the voyage progresses. At launch, the ship can communicate with mission control in near real time. Telemetry flows back. Commands flow forward. Engineers on Earth can monitor the ship's health and send instructions. But as the ship moves outward, the communication delay grows. At 1 light year, messages take a year each way. At 2 light years, 2 years. By the time the ship is halfway to even the nearest star, the round-trip communication time exceeds 8 years. The practical consequence is that communication with Earth ceases to be useful for operational decisions very early in the voyage. If the ship detects a problem and reports it, Earth's response arrives years later. By then, the situation has resolved itself for better or worse. The ship's autonomy is not optional. It is imposed by physics. The speed of light does not accommodate the needs of a sleeper ship's maintenance schedule. This means the ship must carry in its own computational systems all the knowledge and decision-making capability it will ever need. Diagnostic procedures for every system. Response protocols for every anticipated failure. Heuristic frameworks for handling unanticipated failures. And the judgment encoded somehow in software. To know when a situation is manageable by the automation and when it is severe enough to justify the enormous risk of waking a crew member from suspension. What emerges from all of this is a picture of extraordinary fragility masked by apparent simplicity. The sleeper ship looks simple from the outside. A hull, some pods, an engine, silence. No bustling corridors, no crowded mess halls, no children playing in rotating habitats. Just a quiet machine moving through the dark. But inside that quiet machine, dozens of systems must operate in continuous, precise coordination, each one depending on the others, each one subject to the slow degradation that time imposes on every physical object, each one operating without the adaptive intelligence of a human operator who could notice, diagnose, and fix problems that the automation was never designed to handle. What makes this picture so fragile is that these systems do not operate independently. They form a dependency chain, a sequence of linked requirements where the failure of any single element can propagate outward and threaten the whole. No system can be evaluated alone. The thermal control system does not merely need to work. It needs to work while the power system is degrading, while the radiators are eroding, while the coolant is aging, while the cryoprotectant is slowly shifting in ways no sensor was designed to detect, while the hull is absorbing micrometeorite impacts, while the sensors are drifting, while the software is accumulating runtime errors, while cosmic rays are flipping bits in the computer memory that controls the coolant pumps. Each of these degradation processes is slow. Each one in isolation is manageable. But they are not in isolation. They are simultaneous. They interact. They compound. And over decades, the cumulative effect of a dozen slow degradations, none of which individually triggers an alarm, can quietly erode the ship's functional margins until the next perturbation, however minor, pushes a system past its threshold. This is not a dramatic failure. It does not announce itself with explosions or alarms. It is a slow, silent convergence of small imperfections that only becomes visible when it is too late to reverse. And it is the most realistic way a sleeper ship dies. Not in a catastrophic instant, but in a long, quiet decline that no one is awake to notice. The ship that carries sleeping passengers through deep space is not a simple container. It is the most complex, unattended machine ever conceived. Asked to perform the most demanding task in the history of engineering, keeping human biology intact across distances and timescales that dwarf anything we have ever attempted. And it must do this alone, in the dark, with no help, no resupply, and no second chance. That is the engineering reality of a sleeper ship. And it raises the question that every engineer dreads, but every mission planner must face. What happens when something in that chain actually breaks? When the alarm sounds and no one hears it? When the cascade begins and no one is awake to stop it? That question is next. And the answers are the reason the sleeper ship, for all its elegance as a concept, is terrifying as a dependency. There is a word that engineers use when they talk about systems that must not fail. They call them single points of failure. A single point of failure is any component whose loss alone is enough to bring down the entire system. Good engineering eliminates single points of failure through redundancy. You install 2 pumps instead of 1. You run 2 independent power buses. You carry backup computers loaded with duplicate software. If one fails, the other takes over. The system survives. Spacecraft design has been built around this principle since the beginning of the space program. The Apollo spacecraft carried triple redundant computers. The Space Shuttle used 4 independent flight computers. The International Space Station has backups for nearly every critical function, and still requires regular resupply from Earth to keep them viable. A sleeper ship would need redundancy at a level that dwarfs anything we have ever built. Not because the individual systems are more complex, though some of them would be, but because the duration of the mission is so extreme that even highly reliable components will eventually fail. A component with a 99.9% chance of surviving any given year still has roughly a 99% chance of surviving 10 years. But over 50 years, that probability drops to roughly 95%. Over 200 years, it drops to roughly 80%. And over 500 years, a component that seemed almost perfectly reliable has nearly a 40% chance of having failed. Now multiply that by the hundreds or thousands of components in a sleeper ship's critical systems. The probability that every single one of them survives the full voyage approaches zero as the duration increases. This is not pessimism. It is statistics. Given enough time, something will fail. The question is not whether a failure will occur. It is what happens when it does. On any crewed spacecraft, the answer has always been the same. The crew responds. They hear the alarm, read the diagnostic, isolate the failed component, activate the backup, and if the backup fails, they improvise. Human spaceflight history is filled with stories of crews solving unanticipated problems because human intelligence is adaptive and creative in ways no automated system has matched. Apollo 13 is the most famous example. An oxygen tank explosion crippled the spacecraft's power and life support. The crew and ground controllers improvised a carbon dioxide scrubber from duct tape and cardboard, keeping the crew alive long enough to return to Earth. The failure was unprecedented. The materials were not designed for that purpose, and the solution required creative reasoning under extreme stress. A sleeper ship has no crew to respond. The alarm sounds in an empty corridor. The diagnostic prints to a screen that no one is reading. The automated system detects the failure and consults its decision tree, a pre-programmed set of responses designed by engineers who tried to anticipate every possible scenario before the ship launched. If the failure matches a scenario in the decision tree, the system executes the planned response, activate the backup, reroute the power, adjust the thermal set point, close the valve. These are the failures the system was designed to handle, and for those failures, automation can be effective. But the failures that threaten a sleeper ship most seriously are the ones that do not match any scenario in the decision tree. The ones that were not anticipated. The ones that emerge from the interaction of multiple small degradations, none of which individually triggers an alarm, but which together produce a situation that no one imagined during the design phase. Consider a scenario. The ship is 47 years into a 90-year voyage. One of the radiator panels on the port side has been slowly losing emissivity due to micrometeorite erosion of its surface coating. The thermal control system compensates by increasing coolant flow to the starboard radiators. This works, but it places additional load on the starboard coolant pump, which has been running continuously for 47 years. The pump bearing, which was rated for 30 years of continuous operation, develops a slight vibration. The vibration is within the tolerance band defined in the system's diagnostic software, so no alarm is raised, but the vibration accelerates wear on the bearing seal. Over the next 3 years, the seal begins to weep coolant at a rate of a few drops per week. The coolant reservoir, which was sized with a modest margin, begins to deplete. The reservoir level sensor, whose calibration has drifted by 4% over 5 decades, reads the level as slightly higher than it actually is. The system believes it has adequate coolant. It does not. 2 years later, The starboard coolant pump seizes. The thermal control system attempts to reroute all cooling through the backup loop. But the backup loop has been dormant for 49 years. When the system pressurizes it, a valve that has been sitting closed for half a century doesn't open cleanly. Its seat has cold welded, a phenomenon where metal surfaces in vacuum bond at the molecular level over long periods of contact. The system applies maximum actuator pressure. The valve cracks open partway but does not seat properly. Coolant flows but at reduced rate. Thermal stability for the preservation pods degrades. Temperature in pod section 3 begins to rise. The rate of rise is slow, a fraction of a degree per day. The medical monitoring system detects the temperature change but interprets it as within acceptable variation for the current mission phase. 2 months later, the temperature in pod section 3 has risen by 4 degrees. For passengers in deep torpor, this is uncomfortable but not immediately lethal. For passengers in vitrification, this temperature excursion has initiated ice crystal nucleation in peripheral tissues. The damage is occurring at the cellular level, invisible to every sensor on the ship. Nobody hears the alarm because there is no alarm. Every system individually reports nominal status. The radiator degradation is within tolerance. The coolant level reads acceptable. The backup valve is registering as open. The temperature rise is within the monitoring system's acceptable band. The passengers are silent and still. And inside their bodies, ice crystals are growing. This is a cascade failure. Not a single dramatic event, but a sequence of small degradations that interact across systems in ways the designers did not fully model. Each link in the chain is a modest problem. Together, they produce a catastrophe. And the defining characteristic of this kind of failure is that it is invisible to the automated systems until the damage is already done. Cascade failures are not hypothetical. They are well documented in complex engineered systems on Earth. Aircraft crashes, nuclear plant incidents, industrial disasters, many of the worst failures in engineering history followed this pattern. Multiple small problems, each manageable in isolation, converging to produce an outcome that no individual failure could have caused alone. The common factor in nearly all of these events is that a human operator, had they been present and attentive, could have recognized the developing pattern and intervened before the cascade reached its terminal stage. On a sleeper ship, there is no human operator. The pattern develops unchecked, and the passengers sleep through their own destruction. The ship's autonomous systems represent the only line of defense, and their limitations must be understood honestly. Current spacecraft autonomy is remarkable by the standards of a decade ago, but primitive compared to what a sleeper ship would require. The most autonomous deep space probes ever built, the Voyagers, New Horizons, Cassini, can detect certain types of failures and switch to backup systems. They can enter safe mode, shutting down non-essential systems to protect critical functions when something goes wrong. They can execute pre-programmed recovery sequences, but they cannot physically repair themselves. They cannot replace a failed component. They cannot patch a micrometeorite hole. They cannot recalibrate a drifted sensor. They cannot clean a fouled radiator surface. They are operationally autonomous, but physically helpless. A sleeper ship would need something far beyond this. It would need robotic systems capable of performing physical maintenance and repair on the ship's structure and systems. Robots that can navigate the ship's interior and exterior. Robots that can diagnose mechanical faults. remove failed components, install replacements, test the repair, and return to standby. These robots must carry tools, spare parts, and the manipulative dexterity to work on systems that were designed to be maintained by human hands. Building such robots is not beyond foreseeable technology. Robotic arms on the International Space Station perform complex maintenance under remote control. Mars rovers navigate autonomously. Research into self-healing materials and autonomous fault detection is advancing steadily. But every one of these robotic repair systems is itself a machine. It has its own components that can fail, its own bearings that wear, its own electronics that degrade under radiation, its own software that can encounter conditions its programmers did not anticipate. The repair robot that is supposed to fix the coolant pump can itself break down. And then the question becomes recursive. Who repairs the repair system? You can add redundancy. Carry 2 repair robots, carry 5, carry 10. Each one is a backup for the others. But each one adds mass, complexity, and its own potential failure modes. And over decades, even redundant repair systems degrade. The spare parts they carry are finite. The raw materials for manufacturing new parts, if the ship carries manufacturing capability, are finite. The repair robot's own components age just as relentlessly as the systems they are designed to maintain. At some point, the redundancy runs out. The spare parts are exhausted. The repair robots have used their operational margins. And the next failure, the one that comes after the reserves are depleted, is the one that has no answer. That is the failure the ship cannot recover from. And on a long enough timeline, that failure is certain. Software and data integrity introduce another dimension of vulnerability that is easy to underestimate. The ship's autonomous systems, everything from thermal control to medical monitoring, to navigation to robotic repair, all run on software. That software must execute correctly, continuously, for the entire duration of the voyage. On Earth, software is updated, patched, debugged, and restarted regularly. Mission-critical software is tested exhaustively before deployment, but even so, bugs are discovered in operational use and corrected through updates. A sleeper ship's software cannot be updated from Earth once the communication delay makes real-time interaction impossible. The software loaded at launch is the software the ship will run for the entire voyage. If it contains a latent bug, a rare edge case that only manifests under specific conditions that happen to occur in year 63 of the mission, there is no patch. If cosmic radiation flips a bit in the computer's memory, changing a 0 to a 1 in a critical variable, the software may begin producing incorrect outputs without any indication that an error has occurred. Radiation-hardened electronics mitigate this risk, but do not eliminate it. Hardened processors are more resistant to single-event upsets, the bit flips caused by high-energy particles passing through semiconductor material. But hardening adds cost, mass, and typically reduces processing speed. And even hardened systems are not immune. Over decades of exposure to the interstellar radiation environment, the cumulative effects of radiation damage on electronic components, threshold voltage shifts, increased leakage current, degradation of transistor performance, slowly erode the reliability of every computer aboard. Error-correcting memory, redundant processor architectures, and watchdog timers provide layers of protection. These are standard techniques in spacecraft computing. But they are designed for missions lasting years, not centuries. The question of whether any computer system, however well designed, can operate reliably for 100 years without human maintenance is genuinely open. We have no experience base for it. The oldest continuously operating computer systems on Earth are a few decades old, and they have been maintained, upgraded, and repaired throughout their lives. A sleeper ship's computers must run unattended in a radiation environment for durations that exceed our entire history of computing. And the software must not only run, it must make decisions. Critical decisions with life or death consequences for the passengers. Should the thermal set point be adjusted? Should a backup system be activated? Should a repair robot be dispatched? Should a passenger's preservation protocol be modified? Should a crew member be revived to handle a situation that exceeds the automation's capability? That last question is the most consequential decision the ship's software will ever face, and it leads us to the most fragile point in the entire sleeper ship concept: revival. Waking a human being from prolonged biological suspension is not like waking someone from ordinary sleep. It is not even like waking someone from anesthesia. It is, depending on the preservation method, a major medical procedure that reverses a physiological state no human has ever been placed in for the durations a sleeper ship requires. If the passenger is in light torpor, revival might involve gradually rewarming the body, administering stimulants to restart normal metabolic function, providing intravenous fluids and nutrition to a system that has been running on minimal resources for months or years. The cardiovascular system must readjust to normal workload. Muscles that have been immobile for extended periods must be rehabilitated. Neurological function must be assessed. Cognitive capability must be verified. Even in the best case, the revived individual is likely to be disoriented, physically weak, and mentally foggy for hours or days after waking. If the passenger is in deep hypothermia, the revival is more complex. Rewarming must be carefully controlled to avoid cardiac arrhythmias, which are a known risk when raising the temperature of a deeply cooled human body. Electrolyte imbalances that developed during the hypothermic period must be corrected. Organ function must be monitored closely as systems restart. The brain, which is extraordinarily sensitive to temperature fluctuations and oxygen disruption, must be brought back to full function without triggering the kind of neurological damage that hypothermia protocols on Earth are specifically designed to avoid. And those protocols assume a hospital full of specialists and equipment. If the passenger is vitrified, revival is an entirely different order of challenge. The vitrified body must be rewarmed rapidly and uniformly to prevent ice crystallization during the thawing process. This is the nanowarming problem that researchers at the University of Minnesota have begun to solve at the scale of a rat kidney. At whole body scale, the challenge is staggering. Every organ, every tissue type, every region of the body must be rewarmed at the correct rate. The cryoprotectant that infuses the tissues must be removed and replaced with normal biological fluids without causing osmotic shock or toxic damage. Blood must be reintroduced into a vascular system that has been glass-like solid for years or decades. The heart must be restarted. Breathing must resume. And the brain, 100 billion neurons with trillions of synaptic connections encoding the person's identity, memories, personality, and skills, must resume function with those connections intact. This has never been done. Not in a human. Not in any whole mammal. The closest analogue is the cryopreserved rat kidney transplant. And that is a single organ, not a person. The gap between recovering a kidney and recovering a conscious human being with intact cognition is the gap between flying a paper airplane and landing a passenger jet. And this revival must be performed not in a hospital with a full medical team, but inside a spacecraft, by automated systems, potentially decades after launch, in a ship that may itself be experiencing system degradation. The revival equipment must work perfectly after years of dormancy. The medical monitoring systems must accurately assess a physiological process that has never been observed in human subjects. The software must make moment-by-moment decisions about rewarming rates, fluid administration, drug dosing, and cardiac intervention without any human physician to consult. If the revival is routine, planned as part of the mission timeline, the ship can prepare. Pre-warm the medical bay, activate the revival equipment in advance, run diagnostic checks on every component. This maximizes the chances of success, to the extent that any untested process can be called likely to succeed. But if the revival is an emergency, triggered by a critical system failure that the automation cannot handle alone, the situation is far more desperate. The ship must revive a crew member while the emergency is ongoing. The revived individual wakes into crisis. They are physically compromised from the revival process itself. They are disoriented, possibly confused, possibly experiencing neurological effects from imperfect preservation. They are standing in a ship they may not fully remember how to operate, having been unconscious for years or decades, and they must diagnose and fix a complex engineering problem under time pressure with limited tools in a spacecraft that is already in trouble. This is the nightmare scenario. Not because it is implausible, but because it is the logical consequence of the sleeper ship's core design. The crew cannot be awake because the journey is too long, but the ship cannot guarantee that it will never need them. And when it does need them, the process of bringing them back is itself a medical emergency conducted inside an engineering emergency. The worst case scenario is quieter than any of these, and for that reason, more horrifying. The ship arrives at its destination. The hull is intact. The reactor is running. The navigation system performed flawlessly. The thermal control maintained temperature within tolerance for the entire voyage. Every system reports nominal. The ship enters orbit around its target world. The revival sequence initiates, and the passengers do not wake up. The preservation failed, not catastrophically, not in a way that any sensor could detect, but silently, at the cellular level, over decades, in ways that were too subtle for the monitoring systems to catch. Perhaps the cryoprotectant degraded chemically over time, losing its protective properties so gradually that no concentration threshold was ever breached. Perhaps slow radiation damage accumulated in neural tissue, disrupting synaptic architecture at a rate below the resolution of any imaging system the ship carried. Perhaps the ice crystal nucleation that began during that 4-degree temperature excursion in year 49 propagated slowly through tissue over the subsequent decades, reaching a level of damage that is incompatible with revival by the time the rewarming begins. The ship did everything right. Every system functioned. The hull held. The power lasted. The navigation was precise. But the contents of the pods are no longer recoverable. The bodies are intact. They look peaceful. But the biology that made them people, the neural patterns, the cellular integrity, the delicate chemistry of life has been irreversibly compromised by time and physics, and the inherent limitations of preservation technology that was never proven for this duration. The ship has become a tomb. A perfectly functioning tomb, arriving on schedule at a world no one will ever set foot on. This outcome haunts every serious discussion of sleeper ships because it reveals the concept's deepest vulnerability. The ship's survival and the passenger's survival are not the same thing. A sleeper ship can survive a century of deep space travel and arrive with its structure intact, its systems running, its destination reached, and every passenger aboard can still be dead. Not because the ship failed, but because the preservation failed. Because keeping a human body in recoverable condition for decades is a problem of biology, not engineering. And biology does not obey the same design margins that engineers rely on. The question of whether a caretaker crew could mitigate these risks deserves honest examination. The caretaker model proposes that a small team of crew members remains awake in rotating shifts, monitoring the sleeping passengers and the ship's systems. Each caretaker serves for a period, perhaps a year or two, before being returned to suspension and replaced by the next caretaker revived from the pods. This partially solves the human oversight problem. A caretaker can inspect systems, perform maintenance, monitor preservation quality, and respond to emergencies in ways that pure automation cannot match. But the caretaker model inherits problems from both the sleeper ship and the generation ship simultaneously. The caretakers need food, water, oxygen, and living space. They need exercise to counteract the effects of microgravity or reduced gravity. They need psychological support to handle the isolation of being the only conscious person on a ship full of sleeping bodies in the middle of interstellar space. They age normally during their watch. They accumulate radiation exposure. They experience the psychological burden of knowing that if something goes wrong during their shift, they alone must handle it. And every rotation, every revival and resuspension of a caretaker is a risk. Each revival is a medical procedure. Each resuspension is a medical procedure. If either fails, you lose a crew member. If the revival process subtly damages cognition, each rotation degrades the quality of the caretaker's judgment. After several cycles of suspension and revival, a caretaker might be physically functional, but cognitively diminished in ways that are difficult to detect and impossible to reverse. The caretaker model is a compromise. It improves the sleeper ship's robustness against the kinds of slow, subtle failures that automation alone might miss. But it does not eliminate the fundamental vulnerability. The caretakers can inspect the systems and the pods. They can catch problems that sensors miss, but they cannot prevent the slow biological degradation that may be occurring inside the preserved passengers at a level below their ability to detect. They cannot guarantee that the passengers will be revivable at the end of the voyage. They can only reduce the probability that something goes wrong without being noticed. And they introduce their own failure mode. What happens if the caretaker system itself fails? If the revival mechanism for the next scheduled caretaker malfunctions? If the current caretaker falls ill or is injured, and there is no one to replace them? If a caretaker makes a critical error in judgment due to stress, isolation, or cognitive decline? The caretaker model trades one set of vulnerabilities for another, without eliminating the vulnerability itself. The underlying truth of the sleeper ship, the truth that no design choice fully escapes, is that its survival is not determined by the strength of its strongest system. It is determined by the endurance of its weakest. The ship is a chain of dependencies, and the chain must hold for the entire voyage. Power must feed thermal control. Thermal control must protect the pods. The pods must preserve the passengers, the sensors must monitor the pods, the software must interpret the sensors, the automation must manage the ship, the repair systems must maintain the automation, and the revival system, the most complex and least proven element of all, must successfully reverse the preservation process at the end, converting silent, motionless, biologically paused bodies back into living, thinking, functioning human beings. Every link in that chain is subject to the relentless erosion of time. Every material ages, every mechanism wears, every sensor drifts, every software routine accumulates edge cases it was never tested against, and no one is awake to catch the slow convergence of small imperfections that precedes a system-level failure. The sleeper ship's survival is measured not by the elegance of its biology or the power of its engines. It is measured by the weakest link in a chain that must hold, unbroken, in silence, in the dark, for longer than any machine in human history has ever been asked to operate without human hands to guide it. And the longer the voyage, the longer that chain must hold. And the longer the chain must hold, the more certain it becomes that somewhere, at some point, a link will give. That is the mechanical reality of a sleeper ship. Not a question of whether failure is possible, but of when it becomes inevitable. And the answer to that question is what determines how long a sleeper ship could actually survive. That calculation is next. We have now covered the full scope of what a sleeper ship would require. The biology of preservation, which remains unsolved for anything beyond short-duration torpor in humans. The engineering of the ship, which must sustain power, thermal control, radiation shielding, life support, medical monitoring, navigation, and autonomous repair for the full duration of the voyage. And the failure modes, the slow, compounding degradations that threaten to erode the ship's systems and the passengers' viability in ways that no one awake can catch and no automation can fully prevent. It is time to answer the question in the title. How long could a sleeper ship actually survive in deep space? The honest answer is that there is no single number. The survival duration depends on the preservation method, the quality of the engineering, the depth of the redundancy, the reliability of the automation, and the acceptable level of risk to the passengers. But we can frame the answer by examining 3 scenarios, each defined by a different journey duration, and assessing what each one demands from the biology and the machine. The first scenario is the short duration mission, 5 to 15 years. A transit to Mars, or perhaps a voyage to the outer solar system. The biology for this scenario is the closest to what current research supports. Light torpor, a modest metabolic reduction induced pharmacologically, maintained for weeks or months at a time with periodic brief arousals. The University of Pittsburgh studies have demonstrated quasi-torpor in human volunteers lasting hours. Extending this to weeks or months is speculative but not unreasonable given the trajectory of current research. The European Space Agency's Concurrent Design Facility study specifically examined torpor for Mars-class missions and concluded it could meaningfully reduce spacecraft mass and crew resource requirements. The engineering is demanding but within demonstrated capability. Cassini operated for roughly 20 years. The Mars rover Opportunity lasted nearly 15 years on the Martian surface. Radioisotope power systems produce reliable output over this time frame with only modest decline. Thermal control, life support, and medical monitoring systems would need to be more sophisticated than anything currently flying. But the engineering principles are established, and the duration is within the design envelope of components that have been tested and proven in space. Revival after months to years of light torpor is the largest unknown. No human has been revived from torpor lasting more than hours, but the physiological distance between hours and months is smaller than between months and decades. Research in animal models suggests that periodic arousals during torpor, brief episodes where the body rewarms and performs maintenance functions before returning to the suppressed state, may be essential for preserving biological integrity over longer periods. A sleeper ship designed for a 5 to 15 year mission might cycle passengers through alternating periods of torpor and brief arousal, each arousal lasting hours or days, managed by the ship's medical systems. This is the most credible scenario. The biology is speculative but grounded. The engineering is challenging but feasible. The duration is short enough that degradation and drift are manageable with reasonable redundancy. A sleeper ship for a 15-year transit might be achievable within several decades, assuming continued investment in torpor research and spacecraft autonomy. Not guaranteed, but plausible. The second scenario is the medium duration mission, 50 to 100 years, an interstellar crossing to the nearest star systems at a few percent of light speed. This is where the sleeper ship moves from engineering challenge to engineering nightmare, and it deserves more careful examination than the other two scenarios because it is the scenario where the answer is genuinely uncertain. It is the boundary between plausible and impossible, the place where the concept is most interesting and most terrifying at the same time. The biology for this scenario enters deeply speculative territory. No form of human preservation, torpor, hypothermia, or vitrification has been demonstrated for anything close to 50 years. The longest demonstrated human metabolic suppression is measured in hours. The longest demonstrated organ cryopreservation with functional recovery is 100 days in a rat kidney. The gap between 100 days and 50 years is not a gap that extrapolation can casually bridge. It spans unknown territory in cellular aging, cryoprotectant chemistry, radiation damage to preserve tissue, and the long-term stability of biological systems held in states they were never evolved to occupy. Could future science close this gap? Possibly. The trajectory of cryopreservation research is genuinely encouraging. The nanowarming breakthrough, the torpor studies, the organoid research, the work on radiation protection through metabolic suppression, all of these are real advances being pursued by serious scientists with serious funding. But even optimistic researchers describe human torpor trials as a decade away. And those trials would involve short-duration experiments, not multi-decade preservation. The science needed for 50-year cryosleep does not exist today, and may not exist for generations. The engineering for a 50 to 100-year mission is where the constraints become severe. Radioisotope generators using plutonium-238 lose half their output in approximately 88 years. A ship launched with a power budget carefully matched to its minimum requirements would be operating on roughly 60% of its initial power at the 50-year mark and roughly 50% at the 88-year mark. Systems must be designed from the start to function at these reduced levels, and the power margin between adequate and inadequate narrows with every passing year. Nuclear fission reactors could provide higher and more sustained power, but they require active management, coolant flow, control mechanisms, and fuel that introduces its own complexities. Operating a fission reactor autonomously for 50 to 100 years without human maintenance, is beyond anything that has been demonstrated or even seriously tested. The longest-running naval nuclear reactors, maintained by expert crews with regular access to port facilities, operate for 20 to 25 years between major overhauls. Asking a reactor to run for 4 times that duration with zero human oversight is asking for something that no reactor engineer today would sign off on with confidence. Material degradation over 50 to 100 years is significant and unavoidable. Seals crack, bearings wear, lubricants break down, electronic components accumulate radiation damage, structural metals develop fatigue from thermal cycling, polymer components become brittle, every material on the ship is aging, and the cumulative effect of all these small degradations converges toward system-level vulnerability. The mathematics of component reliability make this concrete. Consider a ship with 500 critical components, each one engineered to an annual survival probability of 99.5%. That sounds excellent. Any single component has only a 1 in 200 chance of failing in any given year. But across 500 components and 80 years, the arithmetic is merciless. The probability that every single one of them survives is 0.995 raised to the power of 500 times 80. That is 0.995 raised to the power of 40,000. The result is a number so small it is effectively indistinguishable from zero. Not one component might fail. Dozens almost certainly will. The question is not whether the ship will face a critical failure over 80 years. The question is how many critical failures it will face, how quickly each one can be resolved by the autonomous systems, and whether any of them happen to strike a link in the dependency chain that has no functional backup remaining. And the passenger's biology faces its own accumulating assault, independent of anything the ship's systems do. At the 75-year mark of a deep space voyage, even with good shielding, perhaps reducing the ambient galactic cosmic ray dose by 60%, a sleeping passenger has absorbed a cumulative radiation dose of roughly 9 to 12 sieverts. For context, a whole body dose of 6 sieverts delivered acutely is almost always fatal on Earth. The exposure aboard a sleeper ship is chronic rather than acute, spread across decades rather than delivered in a single event, which changes the biological impact significantly. Chronic exposure allows some degree of cellular repair between hits, and the fact that the passengers are metabolically suppressed may slow the propagation of radiation damage. But even accounting for these factors, 9 to 12 sieverts over 75 years means extensive DNA damage throughout the body, elevated mutation rates in every tissue, and a genomic landscape at the destination that is measurably different from the one at departure. Whether the revival process can succeed in a body whose cellular machinery has sustained this level of cumulative damage is a question that no experiment has ever addressed, because no experiment has ever operated on this timescale. The probability of a critical failure occurring somewhere in the ship's systems over a 100-year voyage approaches certainty. Redundancy extends the window, but redundancy is finite. Backup systems that sit dormant for decades may not function when called upon. Cold welded valves, degraded seals, corroded electrical contacts. The dormant backup is not guaranteed to be a working backup when the moment arrives. This is the scenario where the sleeper ship concept becomes theoretically conceivable but practically terrifying. Everything must go right. Every system must hold. Every backup must work. Every autonomous decision must be correct. And the revival process, which has never been attempted after this duration in any organism, must succeed perfectly at the far end. The margin for error is not thin. It is essentially non-existent. The third scenario is the extreme duration mission, centuries to millennia, reaching distant star systems or crossing major interstellar distances at modest fractions of light speed. This is the scenario that science fiction has made most familiar, and it is the scenario that honest engineering assessment renders essentially impossible with any foreseeable technology. The biology is pure speculation. There is no scientific basis for believing that a human body can be preserved in a recoverable state for centuries. Vitrification, the most promising cryopreservation approach, has been demonstrated for 100 days in a single rat organ. Scaling from that, the whole body preservation of a human being for 300 years involves leaps across multiple unsolved problems, any one of which could be permanently intractable. The chemistry of cryoprotectant agents over centuries is unknown. The behavior of vitrified human tissue under continuous cosmic radiation exposure over centuries is unknown. The long-term stability of neural synaptic architecture in a vitrified brain over centuries is unknown. We do not merely lack answers to these questions. We lack the experimental frameworks to begin asking them meaningfully. The engineering is similarly beyond any credible projection. No power system, no structural material, no computer, no autonomous system has been demonstrated to operate for centuries without human maintenance. The Voyager probes, our longest-running deep space machines, are approaching their operational limits after roughly 50 years, and they are incomparably simpler than any sleeper ship would need to be. Asking a spacecraft to function autonomously for 500 years is not asking for an improvement over current technology. It is asking for a category of reliability that has no precedent in the history of any human-made machine. Consider what has happened on Earth over the last 500 years. In 1526, the Ottoman Empire was at its height. The printing press was a recent invention, and the first circumnavigation of the globe had only just been completed. Every machine built in that era has long since crumbled. Every building from that period that still stands has been continuously maintained and repaired by generations of human hands. The idea that a machine built today could function without maintenance for an equivalent span of time in the harshest environment known to exist is not engineering optimism. It is a statement of faith. A sleeper ship designed for a multi-century voyage would need breakthroughs in every domain simultaneously. Biological preservation that works for durations orders of magnitude beyond anything demonstrated. Power systems that maintain output for centuries. Materials that resist degradation for centuries. Computers that operate correctly for centuries. Autonomous systems that can handle any conceivable failure for centuries. And a revival process that can reverse centuries of biological suspension and return a functioning human being. Any one of those breakthroughs would be among the most important achievements in the history of science. All of them together, integrated into a single functioning system, represent a technological horizon so distant that responsible assessment cannot distinguish it from impossibility. So, where does this leave us? The credible survival window for a sleeper ship, based on current science and foreseeable technology, ranges from plausible at the short end to speculative in the middle to essentially impossible at the extreme. A 5 to 15 year mission using light torpor is within research reach. A 50 to 100 year mission using advanced cryopreservation is imaginable but unproven. A multi-century mission is beyond any honest engineering projection. The survival limit of a sleeper ship is not set by the human body alone. It is set by the weaker system in a chain of interdependent systems that must all function for the full duration. The biology, the power, the thermal control, the shielding, the monitoring, the automation, the repair capability, and the revival technology each impose their own maximum duration, and the shortest of those maximums defines the mission's outer boundary. If you could solve the biology perfectly, giving us a preservation method that holds a human body in recoverable condition indefinitely, the ship's engineering becomes the limit. If you could solve the engineering perfectly, building a spacecraft that maintains itself autonomously for centuries without degradation, the biology becomes the limit. And if you could solve both, the revival process, the most complex and least proven element of the entire concept, becomes the final and most fragile gate through which everything must pass. It is worth asking whether the answer lies in neither concept alone. The pure sleeper ship and the pure generation ship may both be insufficient for the same underlying reason. Each one places the entire burden of survival on a single domain, machines or people, and asks that domain to perform flawlessly for durations that exceed any demonstrated capability. The sleeper ship trusts the machine absolutely. The generation ship trusts human society absolutely. And both trusts, examined honestly, are fragile. The more realistic interstellar vessel might be something that has no clean name yet. A hybrid. A ship that carries a large population in biological suspension and a small population awake. Not a single caretaker cycling through the pods alone, which we examined earlier and found to be dangerously fragile, but a genuine living community, perhaps a few hundred people, maintaining the ship, raising children, transmitting knowledge, and overseeing the preservation of a much larger sleeping population. The awake crew provides the adaptive intelligence, the improvisation, the human judgment that automation lacks. The sleeping population provides genetic diversity, specialist expertise to be revived at the destination, and a hedge against catastrophic losses in the awake community. This hybrid inherits challenges from both parent concepts. The awake community must be large enough to sustain itself across generations, but small enough that the ship's life support can manage the load. The sleeping population must be preserved through whatever duration the voyage demands, with all the biological and engineering uncertainties that entails. The governance structure must address the relationship between those who are awake and those who are not, including the profound ethical question of who decides when and whether to wake them. But it also inherits strengths from both. The awake community can repair systems, monitor pods, detect the slow failures that sensors miss, and maintain the culture of technical knowledge that keeps the ship alive. The sleeping population reduces the total life support burden, carries diversity the awake community cannot sustain alone, and provides a reserve of capability that can be activated when the mission reaches its destination. Neither group carries the full weight of survival alone. The burden is shared between human resilience and mechanical endurance, each one compensating for the other's weaknesses. Whether this hybrid is the correct architecture for interstellar travel is a question for a future that has solved problems we have not yet fully defined. But it suggests that the answer to the sleeper ship's limitations may not be more engineering, and the answer to the generation ship's limitations may not be more social design. The answer may be both, combined deliberately, each one shoring up the vulnerabilities of the other. It is worth comparing the sleeper ship directly with the generation ship one final time to understand what each concept truly offers and what each one sacrifices. A generation ship keeps its passengers awake and active for the entire voyage. It accepts the enormous costs of sustaining a living civilization aboard. Food production, water recycling, air management, governance, education, culture, reproduction, conflict resolution, knowledge transmission, all of it must function for centuries inside a sealed environment. The generation ship's greatest vulnerabilities are human: social collapse, governance failure, knowledge loss, genetic bottlenecking, psychological deterioration, mission drift. These are problems of people, not machines. A sleeper ship removes all of those human problems by removing the humans from active participation. No one is awake to argue, to despair, to forget, to rebel. But in doing so, it transfers every survival function to the ship itself. The machine must do everything the crew would have done, and it must do it without the crew's adaptive intelligence, without the crew's ability to improvise, without the crew's capacity to notice the subtle wrongness that precedes a catastrophe. The generation ship bets on human resilience. Can a community of people hold together, maintain their knowledge, sustain their purpose, and keep their ship running across centuries of isolation? The sleeper ship bets on mechanical endurance. Can a machine maintain itself, preserve its cargo, navigate the void, and perform a medical miracle at the far end, all without a single conscious mind to guide it? Neither bet is safe. Neither concept solves the fundamental problem of deep space, which is that the distances are too vast, the durations too long, and the environment too hostile for any system, human or mechanical, to guarantee survival. The generation ship and the sleeper ship choose different ways to be vulnerable. They choose different things to trust, and neither trust is fully justified by the evidence we currently have. The core thesis of everything we have discussed tonight can be stated plainly. A sleeper ship could survive only as long as its preservation systems, power supply, shielding, automation, and revival technology remained functional. Putting humans to sleep does not remove the danger of deep space. It transfers survival from the crew to the machines, keeping them unconscious. And that transfer carries a weight that is worth sitting with for a moment. Because a sleeper ship asks something of human beings that nothing else in our experience has ever asked. It asks them to surrender everything. On a generation ship, you are at least alive. You are awake. You can see the problem developing. You can argue about the response. You can grab a wrench and try to fix the pipe. You can hold your child and tell them it will be all right. You have agency. You have choice. You have the ability to act, however limited, in the face of whatever the void throws at you. Your survival depends on you, on your community, on the people around you. That dependency is frightening, but it is also deeply human. We've depended on each other since we came down from the trees. We know how to do this, imperfectly, sometimes catastrophically, but we know. A sleeper ship strips all of that away. You close your eyes, the pod seals, the temperature drops, and from that moment forward, you are not a person. You are a biological specimen. You have no awareness, no agency, no ability to respond to anything that happens around you. You cannot hear the coolant pump failing. You cannot feel the temperature rising. You cannot see the ice crystals forming in your own tissue. You have surrendered your survival entirely to the machine that surrounds you, and you have done so with the full knowledge that if that machine fails in any of 1,000 ways, you will never know it. You will not wake to an alarm. You will not have a moment of fear or a chance to fight. You will simply never wake at all. That is the bargain of the sleeper ship. Not sleep in any way that word is normally understood, but a voluntary abandonment of consciousness, agency, and every human capacity for self-preservation, placed in trust with systems that cannot care whether they succeed or fail. The passengers of a sleeper ship are not travelers in any meaningful sense. They are cargo. They are the most precious cargo ever transported. Cargo that must arrive not merely intact, but alive. Not merely alive, but conscious. Not merely conscious, but cognitively whole. But cargo nonetheless. Carried, not carrying. Delivered, not arriving. Subjects of the journey, not participants in it. And the ship is not carrying them the way a vessel carries goods across an ocean. It is carrying them the way a hospital carries a patient in a coma. Every moment of the voyage, the ship is performing a continuous act of medical intervention, holding bodies in a state they would not naturally occupy, monitoring them for complications, ready, in theory, to respond to emergencies. But unlike a hospital, the ship has no doctors awake to consult, no specialist to call, no ability to transfer the patient if things go wrong. The ship is the hospital, the doctor, the nurse, and the pharmacist. And the patients cannot tell it if something hurts. This is why the question of how long a sleeper ship could survive is not really a question about engineering alone. It is a question about what we are willing to trust. What degree of dependency are we prepared to accept? What level of helplessness can we tolerate in exchange for the possibility of crossing a distance that would otherwise be uncrossable? The answer may change as technology advances. It may change as our understanding of human biology deepens. It may change as we develop autonomous systems that are genuinely capable of managing the complexity of a century-long medical intervention in the void. But the fundamental shape of the question will not change. The sleeper ship will always require its passengers to surrender everything and trust that the machines will bring them back. And the machines will always be subject to the slow, relentless degradation that time imposes on every physical object in the universe. Time does not care that the passengers are sleeping. Time does not pause because metabolism has been suppressed. The reactor still decays. The seals still crack. The cosmic rays still penetrate the hull and pass through silent bodies. The coolant still ages. The sensors still drift. The software still accumulates runtime artifacts in memory that no one will ever clear. Sleep does not stop time. It only hides it from the sleeper. And that is the deepest truth about the sleeper ship. The one that separates it from every comfortable science fiction depiction of passengers waking refreshed in orbit, around a distant star. A sleeper ship does not conquer time. It does not cheat time. It does not shortcut around the brutal machine survival problem of deep space. It gambles. It gambles that the machines can outlast the duration, that the power will hold, that the cooling will stay precise, that the shielding will remain effective, that the sensors will stay calibrated, that the software will keep making correct decisions, that the materials will resist the decay that physics demands of every object, and that at the far end of all those decades of silent, unmonitored mechanical endurance, the revival process will work. That gamble might pay off for a 15-year Mars transit. The odds are not terrible. The duration is short. The technology is almost within reach. The biology is speculative but grounded. For a century-long interstellar crossing, the gamble becomes harrowing. The odds lengthen. The unknowns multiply. The chain of dependencies stretches to its breaking point. Every system must hold for a duration that exceeds our experience with any comparable technology. And the revival must work after a period of preservation that has never been tested in any living thing. For a voyage of centuries, the gamble is not a gamble at all. It is an act of faith, placed in machines that have not been invented, running on principles that have not been discovered, preserving biology through mechanisms that have not been demonstrated, for durations that exceed the lifespan of every human-made object in history. The nightmare of a sleeper ship is not being awake for the journey. It is trusting a machine to preserve the human body through deep space and still know how to bring it back. The generation ship asks people to endure the journey as human beings, awake, aware, suffering and adapting and holding together. The sleeper ship asks them to stop being human for the duration and trust that the machine can reassemble what was paused. And reassembly is the word that matters, because that is what revival truly is. Not waking up. Reassembly. The reconstruction of a living, thinking, feeling person from a body that has been held in a state of biological suspension by artificial means for a duration that biology never intended. Every cell must resume its function. Every organ must restart its processes. Every neural pathway must reconnect. The person who opens their eyes at the destination must be the same person who closed them at departure, with the same memories, the same personality, the same capacity for thought and feeling and choice. Anything less is not revival. It is something else, something that looks like the person but is not fully them. And we do not even have language yet for what that something else would be. A sleeper ship is not a shortcut around survival. It is survival placed entirely in the hands of systems that cannot be allowed to fail. And the deeper we look at what that means, the more clearly we see that sleep does not solve the problem of crossing deep space. It only changes who bears the burden. On a generation ship, the people carry themselves. On a sleeper ship, the machine carries them. And in the end, the question is the same. Can anything we build, whether it is a civilization or a machine, endure long enough to cross the distance between the stars? We do not know, not yet. But the fact that we are asking the question, that we are studying torpor and vitrification and autonomous repair and nanowarming and radiation protection, that we are building the science piece by piece, even though the whole is still impossibly far away, that fact says something about us that is worth honoring. We are a species that looks at a 25 trillion mile void and does not accept it as final. We look for ways across, even the desperate ones, even the terrifying ones, even the ones that ask us to close our eyes and trust the dark. The stars are patient. They will wait. And when we are ready, whether we cross the distance awake or asleep, the crossing will be the most extraordinary thing our species has ever done. But we should go with our eyes open, even if the plan is to close them. We should understand what we are trusting, what we are risking, and what we are asking of the machines that will carry us. Because the ship does not dream, the ship does not hope, the ship does not know what it is carrying. It only knows what it was told to do. And in the silence between the stars, that will have to be enough. Good night.